So today we'll cover 16.5 and curl and divergence. We'll start with the curl of a vector. And so the curl of a vector is a vector. I have to point that out. The curl of a vector, we can think it's vector field, will be a vector. It's defined as del cross F. Okay, what the heck is del? Up until now, I've always been writing this del with like a function like this, like gradient of a function. But this is the first time that I'm referring to the del alone. So make a note, when I'm talking about del, I'm just saying delta x, or delta y, or delta z, or if you want to call these d's, ddx, dy, ddz. So if we had a vector field, let's say F equals, I'll give you one. I'm actually taking this example from the book. Let's say the vector field is xz. All right, there's the x component. It's three-dimensional, x, y, z. And negative y squared. We're going to find the curl of this vector field. Well, it's going to be a vector. So we'll get the curl and it'll be a vector. If you're curious what this is, people always ask. I want to read this section from the textbook. They said the curl vector is associated with rotation. For instance, when F represents this big F. When F represents the velocity field in fluid flow, particles near a point like x, y, z in a fluid tend to rotate about the axis that points in the direction of curl of F, which we're going to find. And the length of this curl vector is a measure of how quickly the particles move around the axis. So they said, for instance, if the curl of the vector field is 0 at a point P, then the fluid is free from rotations at P and is called irrotational at P. So it would have no rotation at that point. So if you're wondering what this is dealing with in terms of like fluid flow. But here's a vector field given to us. We're going to find the curl of F. Well, it's defined as del cross F, the cross product of del cross F. So this is del, just del F. So I'm going to write out the matrix. How we always found the cross product of two vectors. I'll put I, J, and K. All right, there's my I, J, and K. I'm going to put the del first. Now, del is just what? ddx, dy, ddz. Or if you want to write delta, x, delta. That's what I'm going to put for del. F is, I got enough room here. This is xz. The y component is xyz, and the z component is negative y squared. And we're going to do this just like we always did a cross product. And the cross product of two vectors is a vector. So, you ready to do the cross product? I'll hide that. What's the derivative of this with respect to y? Subtract the partial derivative of this with respect to z. That's what we'll put right here.
So negative 2y.
All right, negative 2y. Subtraction.
With z, right? You said? So
Yeah, the partial of that with respect to z.
xy.
xy. And here's my first component. We're finding the curl of vector field F. Okay, cool, got it. The middle component, isn't that where we change the sign? So I'm going to get ready, like negative. Get ready, all right, wipe out the middle column. What's the partial of that with respect to x? Well, like that.
xy squared?
What's the partial of negative y squared with respect to x? Doesn't have an x in it.
So
0, right?
0, yeah.
All right, so we'll get 0 subtraction the partial of that with respect to a z. X. So I get 0, I'm going to write it, minus x. So everyone knows I actually got a 0 when I did that. So let me see when I wipe out that middle column. Partial of that with respect to x minus partial of that with respect to z. And how about the last component? We'll wipe this k column out, get that out of the way. What's partial of that with respect to x minus the partial derivative of that with respect to y?
yz.
Yz minus 0. I like it. You just found the curl of vector field F. I guess I could simplify it a little bit. What? Negative 2y minus x, y, x, right? And that's just x. And then y, z. That's just the curl. Is that okay with that? Well, we'll do something also today called the divergence, but we're going to stick with the curl for a while because it can be very helpful. It can be very helpful. Remember the word conservative vector fields?
Mm-hmm.
Good. So it comes into play with conservative vector fields, the curl. Here it did. Like, that wasn't so great. But I'm going to be curious. We'll look at some vector fields that might be conservative. So can I erase this? Try this one now. How about x squared, y squared, z squared? Just to do them up. So sometimes you get expressions like we just saw. But sometimes it comes out a lot easier. When the answer, I could say, would be more simple. So let's find the curl of this vector field. The vector field x squared, y squared, z squared. Well, I got my delta, delta x, delta, delta y, delta, delta z. That's my del. And then I'll put the vector field f here. X squared, y squared, z squared. Let's find the curl of this vector field. So the curl of vector field f is, first component, wipe that out. What's partial to x respect to y minus partial to x respect to z?
0, 0.
I love it. Cool. I like it. Makes the math easier. This is the one where we're going to change the sign, so I'm going to get it ready. Now, what's partial to that respect to x minus partial to that respect to z?
Same, 0, 0.
0. And how about that last component?
Same, 0, 0.
Yeah. Partial to that respect to x, 0. Minus partial to that respect to y.
0.
So this came out to be what we call the zero vector. And you can write it like that. Unless you want to write 0, 0, 0. We call it the zero vector. Well, there's a connection between conservative vector fields and the curl of the vector field. And here it is. And I think we should prove it. I'm going to make a statement, then we'll prove this. And if the curl of a vector field, bless you, if the curl of a vector field is 0, that means that vector field is conservative. Boy, is this awesome, because it gives us another way to check three-dimensional vector fields, and whether or not the vector field is conservative. Remember we were doing that last class? It's easy when you just have two-dimensional vectors. You know, we just check take that partial derivative, take that partial derivative, see if they're equal. But when it's three, we always had to do 3 checks. Remember that?
Mm-hmm.
So we got a great way now. We're going to say, if the curl of the vector field is 0, then we know that that vector field is conservative. Now, we have to review something. I keep saying that. Students sometimes will go, time out. What is the definition of a conservative vector field? So I want to point out the definition of a conservative vector field is this. That the vector field is equal to the gradient of some functions. That's its definition. So I want to point out, this is what it means for a vector field to be conservative. That f equals del f. That's the definition of f being what? Is conservative. What do you mean for a vector field to be conservative? I'm saying there's a potential function that will exist, such that the partial derivatives of that function is equal to that vector field. That's another way to say that, but here's a very simple way to look at it. So when you agree, here I could write that, because of what we got. Remember what I said? If the curl of that vector field is 0, then that means the vector field is conservative. Which one this one is, that means some function of f, a function f of x, y, and z must exist. So can we just quickly find that function? It shouldn't be too hard. And when this must exist, there must be some function of x, y, and z. This must exist. I'll put exists. It has to. Because the vector field is conservative. We showed that by getting this equal to 0. But can you find this function of x, y, and z? Remember what to do? This is where you integrate. We're saying these are we're saying this is the partial with respect to x, that's the partial with respect to y, that's the partial with z of some f. So you can integrate that with respect to an x. What would you get? X cubed over what?
3.
Well, now integrate that with respect to y. If you get repeats, toss them. Let's integral that with respect to y.
Y cube over 3.
Alright? And lastly, integral of x by z. There you go. That's the function. I'll put constant k. Constant k. That's the function. That's the function. But that means we knew it existed because the curl of f equals 0. So can we do something? This is fun. Can we prove that the statement, if the curl of a vector field is equal to 0, or, excuse me, let me say it again. Can we prove if the vector field f is conservative, the curl of f equals 0? Let's do that. We're going to do a math proof. So here's our proof. We're going to prove this. When you do proofs, it helps you remember this. So we're going to prove the statement if some vector field is conservative, comma, the curl of a vector field, which is a vector, will always equal what?
0.
0. And I'm going to put a little vector symbol on it, because it's really a vector, so 0 vector. All right, let's prove that. We just saw what happened. We noticed that the function did exist. Well, let's prove this. If the vector field is conservative, the curl of f equals 0. So I start with the curl definition. What's the curl of f? So I'm going to start there. Curl of f equals del cross f. If we're finding a curl of one, we got to start with the definition of the curl of a vector field. So far, so good? Every little proof has a crux move to it, where you slip in one little thing, and that proof's going to be real easy. Here's the crux move. If f is conservative, what does that mean? I'm going to go off to the side. If f is conservative, that means, I'll write this again, that f is equal to a what? Yeah, the del of f. Or gradient of f. If you like to put gradient of f, G-R-A-D, the gradient of some function. The gradient factor of that function. So, do me a favor. Substitute this right here. Aha, that's the crux move to the proof. Let's do the math on this. And let's see what we get. Alright, this is fun. I think you'll find it to be an easy proof. I'll line it up. I, J, K, okay. Delta X, delta Y, delta Z. Now there's a couple ways I can write del F. I can write delta F, delta X, delta Y, and delta F, delta Y, and delta F, delta Z, right? I'm going to write that, but I'm going to erase it. I think you'll find it easier with the other notation. So I can write it like this. The book does that. But isn't that del F right there? I'm going to write it like this, though, because I think the writing, when it comes to our writing, when we write this proof, I think you'll find this easier. How about we just do this? That's easy to write. Let's write it that way. I just think it's easier. Are you ready? Get this curl. All ready. If f is conservative, prove that the curl of the vector field would always be 0. Are you ready? Wipe this out. The partial of this with respect to a y. Oh, I know what that means, right? That would be this. Minus the partial of this with respect to a z. Did everyone see what I just did?
Mm-hmm.
I'm going to do it again. So you go, what am I doing? I'm going to take the partial of this with respect to y. That means the second partial derivative. I'm going to take the partial of this with respect to a z. That's the second partial derivative. So I get that. Does anybody notice something already?
Conservative, yeah.
Yeah, these are equal. Pythagoras theorem, that's 0. Watch what happens in the middle. It's just going to continue, everyone. You ready? Wipe this out. FCX minus FXZ. And down in the third component, look what you get. FYX minus FXY. And by Clairaut's theorem, there you go. What do you get? We get, this is what? 0? What's that? Negative 0, which is 0. And this is what? 0. We proved it. Here we can put a QED. Quite elegant. We can put the math column in a symbol. We ended the proof. There we go. That shows that it's a 0 vector. The curl of the vector field is 0. Isn't that cool? So this is a great way of when now we have a great check to see, hey, is the vector field conservative? Let's find the curl of the vector field. I do point out it must be a 3-dimensional vector to do this because we're doing a cross product. So if you wanted to do it with a 2-dimensional vector, just make the z component a 0, right?
Mm-hmm.
You can do that. All right. So erase this, erase this, erase this. Great job with the proof. By the way, in terms of notes, I did put the proof on the back side of those notes if anybody wants to see it. Because it's such a cool proof. Easy to do. I'm going to leave that up there. But I'm going to start with a problem from the practice problem. And the question is, can you determine whether or not the vector field is conservative? All right. Determine whether or not and I'll do number 15. Is conservative. I wrote be clear in your justification. Okay, we'll justify it. And there's a part B. If the vector field is conservative, if F is conservative, find a function such that F, vector field F, is equal to del of lowercase. Okay. Again, remember that del F just means the gradient of a function. It's a vector. And the vector field I want to give you. Here it is. I'll do a couple of these. All right, let me copy this. X, Y, Z to the 4th. Comma. X squared, Z to the 4th. Comma. 4x squared. Y, Z, and slide. Y, Z cubed. 4x squared, Y, Z cubed. X squared, Z to the 4th. X, Y, Z to the 4th. Can you determine whether or not the vector field is conservative? What's your problem solving strategy? What could you simply check? Find the curl, right?
Mm-hmm.
Find the curl of F, and if the curl of F is 0, the answer is yes. True? Yeah, I do want to point out, some students prefer for some, and it's fine. They go, can I do it like we did in the last lesson? And I go, what do you mean? They check, they thought of this as like a potential one. They go, can I look at this like the last lesson where that was maybe a potential fx, this was a potential fy, and this was a potential fz, and they go, can I just show 3 checks and show that, you know, if fxy must equal fyx, what were the other 2 pairs? fxz has to equal fzx, and thirdly, fyz must equal what? They go, can I go through that? And I go, sure, but do you recognize something? Isn't that like doing the curl?
Yeah.
Yeah, so whatever's easier for you. Most students decide, I'm just going to do the curl of vector field, and if it comes out to be 0, the answer is yes. If it doesn't come out to be 0 in terms of 0 vector, it's no. But I do have some students that really think, they're like, I find this easier. I go, okay. I mean, if you really think about it, it's probably the same amount of work. Okay. All right, let's get to work. IJK. DDX. Well, I better give some more room, huh? I want to make sure I can fit all those components in here. IJK. DDX. DDY. DDZ. Way over here. Okay. X, Y, Z. X squared, Z, and 4x squared, YZ. 0, 0? The answer is yes. We'll move on to letter B. If it's not, we can't do B. We can't do B. All right, wipe this out. What's the partial with that respect to y?
4x squared z cubed.
4x squared z cubed. Subtraction sign. That made the partial with that respect to z.
4x squared z cubed.
4x squared z cubed. Hey! Maybe this is conservative. That's 0, isn't it? Try the middle component. Negative. What's partial with respect to x? 8x y z cubed. Minus, what's partial with respect to z? 8x y z cubed. Hey, this is looking pretty good so far. 8x y
That
z
should be
cubed.
4x squared z cubed.
Ah. So this has come out to be what? I'm going to do this again. We did this times this, right, for this middle component. 8x y z cubed, then we took the partial with respect to z here, and we got what? Only 4x y z cubed. Should I keep going?
No.
Stop right here. Not conservative. Isn't that cool? F is not conservative. So we can't do B. That's impossible. You can't find a function such that F equals del F. It's impossible. F is not conservative. Great job. Hey, try another one. Oops. Well, we know we're going to do the curl. I can leave that up here. This is number 16. Y squared z cubed. Y squared z cubed, comma, 2xy z cubed, and 3xy squared z squared. 3x y squared z squared. By the way, I've had some students, you know what they do first? Because you're all getting a curl right now, right? I've had students in the past where they're like, I'm just going to try to integrate everything the way we usually do. If I can create that function, I know I'm right. I'm like, you got a pretty good argument there, but this is an absolute what? This is an absolute way. Just get the curl of f. Show that it's 0. You know that vector field is conservative. All right. Run it out. I, J, K. dx, dy, and d to z. Y squared z cubed, 2xy z cubed, and this last component is 3x squared y squared z squared. I want to double check I copied that correctly. 3x, no, that's just 3x, right? And that's 2xy z cubed, that's y squared z cubed. Okay, we're ready to roll. What do you get for the first component?
6xy z squared.
6x. Take the derivative of this with respect to x. Let me use this one to wipe that out. What's the partial of that with respect to x?
6xy z squared, right?
Oh wait, we're doing a derivative with respect to the x. Wouldn't the x go away?
Oh, you're doing it at x?
With respect to x, right? Because we'll do d dx of this, or delta x of that, and then we'll do the partial of that with respect to z.
Should we start with the
No, shouldn't start at the...
Oh, I like that. We don't have to start with the middle component. You're like, start with that first one.
Yeah.
Yeah, I agree. So very good. I'll wipe this out. Let's partial that with respect to y. 6x
y z squared.
y z squared minus,
6xy z squared.
and the derivative of that with respect to z is 6xyz squared. Is that 0?
Yep.
Cool.
Why did you do it with the respect to y on the first one?
Oh, great question. So for this one, I'm going to get the first component. I'll wipe out the first column. So I have to do that with respect to a y. And then I'm gonna have to do that one with respect to a z. Good question. And I agree with everyone, when I'll start with that middle component, that's not the best idea. That can make us get confused, so I'll start right there. I'm gonna make sure to start with that. Wipe out the first column and get the first component. Hey, the middle component, I'm gonna put the negative. And what do you get?
Negative 3y squared z squared minus 3y squared z squared.
3y squared z squared minus 3y squared z squared, which is also 0, I'm agree. And how about this last component? So I'll wipe out that one.
2yz cubed.
2yz cubed.
Subtract.
Subtract 3, 2yz cubed. What did we all get? 0? 0? 0? What's the answer? Is that vector field conservative?
Yes.
Yes. Yes. F is conservative. It's a conservative vector field. Was that okay with that? By the way, I know all that writing takes a while, so if you just want to write 0, 0, 0 in a test, that's totally fine. Now, let's move on to letter B. This is possible. It is definitely possible. We got to find F. Find the function such that vector field F is equal to the gradient of some function F. How do we do that? Derivative or integrals? Integrals. So we're going to integrate that with respect to x, put a plus. Integrate that with respect to y, put a plus. Integrate that with respect to z, put a plus. If you get any repeats, toss them. Don't forget about tossing any extra repeats that appear. So I'm going to get this thing started. It's funny because sometimes you're on a test and you start writing like, and you go, wait a minute. They want to what? Find the function. So I'm going to write function of x, y, and z. Equals, all right, go ahead and do that. What's the integral of that with respect to x?
X.
Outstanding. Notice that when we just did an integral, an antiderivative. Okay. It's a partial antiderivative. What's the partial antiderivative of this with respect to y? 2xy squared over 2 z cubed. Or, that's the same as just what? Is that that?
Yeah.
Oh. Anyone notice that? That's a repeat. So leave the first one. I can be careful when I say this. I say toss out repeats. People think you toss out a both. No, keep one of them. Keep the very first one. Bless you. We'll knock out any remaining ones. What do you get here? Partial root of x, or the antiderivative. Integrate this with respect to z. 3xy squared z cubed over 3. And these cancel. Is that a repeat?
Yes, another repeat.
Another repeat. So this was a repeat. We got rid of it. This repeated. That's that same expression. Plus constant. This is it. So I'll write it again. Here's the function. Write it neatly. Okay, it's xy squared z cubed plus k. And you could always take time in a test to double check this by taking what? Take the partial with respect to x, you should get that. Take the partial with respect to y, you should get this. Right? That we can check to see you didn't miss anything. Hey, can I extend this? I want to connect something that we did yesterday. I'm going to ask you to compute a line integral. Oh gosh, line integrals take time. Hold up though. Line integrals are pretty easy if the vector field is conservative. So when I was wondering, could you find, I'm just going to extend this. Can you evaluate f, ooh, no, I can now write del f. Del f dot dr for this vector field, okay? Where C is, I'm going to choose some kind of path. How about a line segment? C is a line segment from the point How about, I'm gonna make up some point in three-dimensional space. How about 2, 0, 4 to the point 3, 1, negative 2. I just chose 2 random points in three-dimensional space. You're like, really? That function can go through those points? Sure. I just picked X, Y, and Z points, right? The function exists at those. This should be real easy. Because by the fundamental theorem of line integrals, if the vector field is conservative, let's use it. What is this equal to? F of endpoint minus F of
Start point.
initial point. I mean, you could write it with the notation. I just think that's an easy way to state it. Take the function you just found, plug in the endpoint, plug in the initial point, and subtract them. We don't have to do all the dot product and all that. Isn't that cool?
We don't need the RT.
I know, because we don't need, because this is really, we could have found it, and then we got R prime and T, then we would have done what? Then we'd taken that vector field, we'd done F dot, that would have been directly. I'm going to put that over here. But it would have taken longer, wouldn't it? And I might have made an error doing all that stuff.
Just yesterday we had to do the tables with like T
Yes!
X and Y values. I just didn't know.
Great question. So in this case, because this was conservative, we're like, this is all we have to do. But if it wasn't conservative, like that very first one, you're right, I would have to use that vector field. And I would think of this as do the integral of f composed of r of t. You and I would have had to create the r of t for that line segment. And then we would have done the dot product with r prime and t d. It would take longer, but this is going to be quick. Everyone, which one's the endpoint? Because the path went from here to here. So what's f of 3, 1, negative 2 minus f of 2, 0, 4? What do y'all get? Plug it in. You go right in there. What's 3 times 1 times negative 2? 3 times 1 squared times negative 2 cubed. Is that negative 24? Yeah? Okay. This looks easier to plug in because of the 0. What do you get? What do you get for your final answer? Reevaluated the line. Isn't that cool? I just thought we could update a topic from yesterday. You go, well, what if it wasn't conservative? It's not so bad, though. Especially with line segments. Because then with line segments, the r prime and t comes out really nice. Go over there? Hey, nice. Okay, so now we're going to talk about the divergence of f. So that's curl of f. Here's divergence of f. div. What's divergence of vector field f? It's going to look like the same formula. Del dot f. There you go. Put that over here. I'll erase all this stuff. Super job with this problem. Super job. What is divergence of vector field f? Divergence
So the dot
of
product.
f is a dot product of del, there's del, with the vector field. So, curl of a vector field is a vector. What's divergence of a vector field?
Scalar.
Scalar. Maybe I should just say that a few times so you don't get confused. Curl of a vector field was a vector. Divergence of a vector field, being a dot product, will always come out to be a scalar, or you can think, the word scalar bugs you, scalar function. It can come out to be a function, like a function of x, y, and z. A scalar function, not a vector field. So, let's try it. Well, I'm going to use something similar that we saw, or simple that we saw earlier today. That when you find the divergence of that vector. Remember, these are vectors. dot product with a vector, you get a scalar function. I'll let you try it. I do want to point out, you will find doing divergence a lot easier than doing curl. Aren't dot products easier?
Uh-huh.
Dot products are way easier. Del. Dot. Okay, well, here's del. What's del?
2x.
D. 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 And if you don't mind, I'm going to put F right underneath. Because you know when we do a dot product, it's this times this plus this times this plus this times this. Do you recall the curl of this vector field is 0? Well, the divergence isn't 0. What's the partial to that in respect to x? Here it comes. So this is divergence of vector field. I get 2x plus 2y plus 2z. That's it. I hope you find divergence real easy to compute. Compared to the curl takes a little more.
What does that measure?
That's a great question. So that's why I wanted to make sure to put this down on a document. I'm going to read this to you. This is from the textbook. You know, what does this represent? The divergence of a vector field represents the net rate of change with respect to time of the mass of a fluid flowing from the point x, y, z per unit volume. So in other words, the divergence of a vector field actually measures the tendency of the fluid to diverge from the point x, y, and z. The tendency of the fluid to diverge from x, y, z. And in terms of our course and the application here, Andrew, Gauss, who was a brilliant mathematician, Gauss came up with just an awesome theorem called Gauss's divergence theorem. The last thing we'll do in this course, where we use this to help us evaluate surface intervals. So that's a really, real huge application. But right now, it's like that's what it does in terms of measuring something. Okay. So we're not good with that? That's the divergence of the vector field. Another. It's funny because divergence always goes fast. Try this one.
But don't you need to dot it?
Oh, go ahead.
Don't you need to multiply them for dot products?
You're right. So I did the derivative of that this times this, but I was thinking, what's the partial of that with respect to x, which is just 2x.
Okay.
And then I just wrote it. So you're right, I did this times this plus this times this plus this times this, but then I evaluated it.
No, but again, you have it with the vector. Don't you have to dot it to the vector, like divergence?
Oh, you're right. I'm going to put a dot right there. But when I dotted it, it was like when we do a dot product,
Oh,
del
okay.
dot that, I'm like, it's this times this plus this times this plus
Okay,
this
now
times
I
this.
see it.
But you are correct, or it's like, I got to do that, multiply to that. But I'm thinking, oh, that would be the partial with respect to x, give me that.
No.
The reason I wrote them underneath each other, because I thought it was easier for you to go, what's that partial with respect to x? What's that partial with respect to y? I could have put this over there, right? Which you absolutely, I could have done this. But you still would have had to do what? This times this, plus this times this, plus this times this. Oops. Hey, so try this one. Now, I hope this goes fast. Give that one a shot. Wipe this out. What's the divergence of this vector? Because it's funny, even in that section, when it's going to be 16.9, Gauss's divergence theorem we'll get. You'll get vector fields like that.
3,
And you'll find that doing the divergence is not too challenging.
3,
3. Partial with respect to x is a what?
1.
Partial with respect to y is a? The partial with respect to z is a? Equals 3. So you notice doing a divergence of a vector field real easy. I mean, even this. What if these were all cubes? I mean, I could have put other letters in there, but these are the kind of things you're going to see. You'll see them in there. Wait, how do I do this again? You might have to go back to your notes just to refer to this. Because this is section 16.5. What do you get for this?
3x squared,
3x squared plus.
y squared plus z squared.
And you'll take this, when we get into section 16.9, we'll do something with that. It's going to help us evaluate some surface intervals. Awesome.
So you said that divergence represents the tendency for a particle to move in a specific direction?
Exactly, and I want to give you a copy of this. Just so, I wanted to write down, like, it's really the wording from the textbook, so you can actually articulate very well and understand exactly what it means. You see that, it's way at the bottom?
You're right. So like, this last one, we got 3 as the final answer, and the one before was an actual function? So
Yes.
is it just like, plug it, like if you had a function, like at this point?
Yes, you said at this point. Good job, man. It would be some x, y, z coordinate. Where in the one where we just got a 3, it would be the same at any point.
Right.
Outstanding. That's where it gets affected by at the point. Matt, very good. Hey, we're now going to do an exercise and determine whether or not we have a vector. We can just put a v. A scalar. We can just put an s. Or if it's just totally meaningless. So can we make up a key? First of all, what does this mean? What's del of f? Del of f is a,
Gradient.
yep, gradient of a function is a vector.
Okay.
So let's just make sure we understand that. Everyone agree? Del of f is vector. All right, what's gradient of function? Isn't that the same thing?
Mhm.
Gradient of function, or grad of f, is vector. This is what you're going to see, and I just didn't want it to bug you. So del f is vector, and notice I do a lowercase f, del of function. These mean the same thing. I got them right there, they're vectors. And when you see a cross product, or a dot product, what it has to be on either side, no matter what. A vector has to be on this side, and a vector has to be on this side. A vector has to be on this side, a vector has to be on this side. And what is vector cross vector?
Vector.
You get a vector. What is vector dot vector? You get a what?
Scalar.
Scale. But anything else, we're just going to say meaningless, okay? So this is page 16.5. I'm going to take the actual problems from the book. They go quick. I won't rush you. There's some tricky ones in here. I want you to be careful with this. Here's the first one. So I'll do all these. They've got A, B, C, D. I think I got enough room. Again, for your answer, you can just write V, S, or how about for meaningless? We'll just put an M. That sound good? Check out letter A. Take it slow. I just know in the past I've done these on tests. And if you didn't go back to review this, they sometimes miss. They're just guessing. I didn't want you to guess. So I'll make sure to give you enough practice here for this. What's a curl of? Is that a vector?
Mhm.
Is that a scalar? Or is that meaningless?
Vector. That's a vector.
Someone's going to catch it.
Meaningless,
How do you know?
because f isn't a vector. so
Yeah,
it's
go on.
not-
Oh, got it. So we're going to add something to that. I know it's tricky, so don't worry. What has to be up to the word curl? Curl of vector field equals vector. So you're like, you can't do curl of a what? Function. So hey, let's add it to our list here. Like this is our key. Let's add it down. And curl, what must be after this word?
Vector.
No matter what, there has to be at least some vector field notation. Same thing with div. What has to be after this div? Has to be a vector. Whereas curl of vector field is vector. Divergence of vector field, but what has to be after that curl? So we're being like, what's our answer letter A?
Meaningless.
This is totally meaningless. But that was tricky, right? I know, because we say f and f, f and f, and that's lowercase f. But curl of a function, nothing. Has no meaning. Super job. Hey, B. Okay, I bet you all get this. GRAD, lowercase f. Gradient of function. That's a vector. Do you all agree? That's a vector. Good. We recognize that gradient of function is a vector field. You can even actually find it. You can find that vector field, right? I'm making up some examples. All right, let's see. They go quick, but slow me down if one bugs you. Wait, how'd that happen? Divergent of f?
Scalar.
You're good. And you all are flying. All right. A was tricky. There's probably going to be a few more. I think they did. No, I don't think this one's tricky. I bet you get this. Curl, parentheses, grad, lowercase f. Gradient of function.
It's a vector.
That's a vector. What's curl
Of a vector.
of a vector?
Vector.
Vector. Meaningless vector, scalar vector. And you're fine, good job. Everyone okay with that? Curl of vector is a vector. That's a vector. This one concerns me. That's the one I worry about. When you stare at us, Brad, way to go. I wouldn't stare at that carefully. Because I keep saying grad f, don't I? I keep saying grad f, gradient f. I keep saying it all over and over, gradient of f. I'm talking about lowercase f, like a function of f. Like that right there. Even me, when I'm writing this on the board, I want to make sure that's that lowercase f for some function of x, a scalar function. Gradient of a scalar function is a vector. GRAD, can you ever have that afterwards? No, it's not like curl and divergence. This is totally what? Meaningless. What has to be right there?
Lowercase.
That has to be a lowercase f. By the way, it can't be del of a vector. It's got to be del of a function, right? And there's del. It's the partial with respect to x, y, and z of some function. Hey, that was good. Any others? Yeah, let's do a few others. GRAD, DIV, F. GRAD, DIV, F. Hey, on the test, I make the vector fields full-face print. So I think that's easier.
Meaningless. That's a meaningless.
Let me start. We're going to take it slow. Do the parentheses first. What's divergence of the vector fields?
Vector.
Divergence of a vector field is a
Scalar, sorry.
scalar function. Now, I say scalar, but you might want to put the word function with it. Think like some scalar function. Like scalar function. You know, like what did we get earlier? X plus y plus z. What we got an x. We had a 3x squared plus 3y squared plus 3z squared. So some kind of scalar function. Well, that's like an f. You all agree? So we're finding the gradient of a.
F, yeah.
This exists, and what is it?
Vector.
This is a vector. So when catch that? We say scalar, but we got oh yeah, like a function, like a scalar function. It can be a constant, but sometimes you get f equal to x plus y plus z or something like that. And this comes out to be a vector. F had meaning it's a vector. You were a vector, you were a vector, you were a vector. Meaningless, scalar, meaningless. Hey, you got it. Hey, we can just do a couple more of these. G, DIV, GRADF. And it's lowercase f. Let's see, what's gradient of function?
This vector.
That's a vector. A vector field like f, right?
Uh-huh.
Does that agree? Gradient of function is a vector. What's divergence of a vector field?
Scalar.
Scalar? This is a scalar. This has meaning. Does that make sense? Excellent. All right, one more. I'm taking letter H. No, we should do more. GRAD, DIVF. Another I. Curl. Curl. of F. What do y'all think? I hope you get this.
Meaningless.
You're the best. Someone see this?
Uh-huh.
That's totally bogus. You can't do that. Divergence of function out. So this right here, totally meaningless because of that. How about this one? Curl of vector field.
That's a vector.
Vector. What's curl of a vector?
Vector.
Vector. You want to table all those? Hey, on the practice sheet, you'll notice I think I did a bunch of those. I figured I knew this is one other area I'm like, I noticed in previous courses, students like, can you give me extra practice for that? So number 14, I did an A, B, C, D, E, F, G, H, I, J, K, L, went down to M just to keep going and going. And you can check them. Just something you could check if you want to do that. It was up to practice as well. So great job with this. So the only thing left we got to do is, can we look at a vector field and get an idea of what's going on with the curl or the divergence? So I'm going to pop up that screen, if you don't mind, just so we can look. And I can write them on the board. These are not hard vector fields to draw, so when I'll put this up, if that screen's bugging you, I'll put it up on the board. That'll work. Let me shrink it a little bit. This is actually number 9 for the textbook. Let me hit the light. And I'll erase this, and eventually I can just copy. This is not a hard vector field to draw on the board. And we can convert it to the board, but I want you to see it on the screen first. Get all this out of the way. We need our definitions. Curl and F. They actually define both. So this is what they're asking you to do. We'll start with number 9. And this will not be a hard vector field for me to duplicate up on that board. But I want you to see it first. Someone see these? Are they blue? Okay. These blue vectors. It looks like this is some vector field. They said the vector field F is shown, but they said it's in the xy plane, as we can tell. But they did say it looks the same in all other horizontal planes. So how about the plane right above?